The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone. So today we have a special talk from Professor Hussein Abbas from University of New South Wales. And the topic is going to be from machine learning to machine education. This is a part of IEEE Day activity. So please welcome Professor Hussein Abbas.
Thank you very much for the introduction. So I will start by making a disclaimer that the contents of this presentation are solely the responsibility of myself and do not represent any official views of collaborators, funding agencies, or the IEEE. So I will be talking to you today about machine education. It's one of the most exciting topics that I am working on at the moment. I will introduce very quickly machine learning. I will be mainly focusing on supervised learning as an example for machine learning. I will tell you how machine learning design and develop machines which can learn. Then I will start introducing machine education, talking about why we need machine education and what is machine education. This is going to take me potentially most of the talk, explaining what is machine education and why do we need machine education and how it works. Then at the end, I will be very quick in explaining a few of the principles that we have designed for machine education, and as well as a couple of use cases in applying some of the machine education methodologies that we have developed to a number of applications. So the majority of the talk will rely on two papers which are going to support the theory. One paper which was published in the Philosophical Transaction of the Higher Society last year, mainly introducing the principles of machine education and also giving an introduction to how we can actually design transparent artificial intelligence and giving some of the basic definitions to unify some of the definitions. The second paper is more on the education side, and it presented one of the framework we use to develop machine education. The other two papers are mainly the case studies paper. One of them was published in the Swarm Intelligence Conference this year, and the other one was published in IGCNN in 2019. So let us start. I will start by talking to you about machine learning and what we mean with a machine that is learning. So the classic definition here, and I'm really focusing on supervised learning, is that I have some inputs, some features which I'm extracting from a situation. So let us take an example. Assume that I am talking about a self-driving car. And I would like to design the image processing system that is able to detect obstacles in an image for a self-driving car. The input here could be simply just the image over time, which means that I have a spatiotemporal input that is coming in a sequence, and I would be feeding this input into a model such as a deep neural network model. That model will generate an output. The output in this case might be there is an obstacle in the image, or maybe there is no obstacle in the image. So at the same time, I would be having labels. I would be having ground truth data. So you will find many of the companies who are working on this problem. They will be having lots of people getting significantly large number of images and labeling these images either automatically or by hand to establish ground truth for the machine learning model to learn. The value of this ground truth is I can compare the output of my deep neural network against the ground truth to calculate an error, and this error is my measure of performance that I would like to minimize. So a machine learning algorithm will simply take this error, will be guided with this error to update the internal weights or the internal states of the models that we have. And this update becomes almost like what we call learning. So the classic definition of learning is, for example, take the definition that I normally use from Mitchell. Learning is the ability of the machine to improve its performance using experience. So what's the experience here? The experience pretty much is this combination of input and ground truth. That's what we call the experience. And the machine is this, normally the machine learning will be focusing on the model architecture. So if we're talking about deep neural network or fuzzy system or learning classifier systems, the model architecture and the representation language that we are using, in addition to this algorithm, which is responsible for updating the internal state of this machine. So what I'm showing you here is a classic cycle for machine learning or specific type of machine learning, which is supervised learning. We can obviously change, instead of talking about this machine could be guided with a reward function. And if it is guided with the reward function, then we'll be talking about reinforcement learning. It could be self-guided machine using some sort of an internal function that automatically guides the machine to update its state, such as in the case of unsupervised learning. It could be, for example, a similarity measure that we are using to do clustering in this case. It doesn't really matter what is guiding this machine. It's still the same principles will hold, that I have experience. In this case, this experience is represented with my data. I have a model which contains both, I have a machine which contains both a model and an architecture, as well as an internal algorithms, which is allowing this machine to continuously update its state so that it improves the performance. And in this case, improving the performance gets indicated through the minimization of this function. Fantastic. So far we are talking really about very, very classic machine learning, and you can see that the focus here is on how I can improve this performance, and because of that, you will find the majority of machine learning papers will be talking about how they improved this error. But now let us start thinking about something in the definition which we haven't really explained, and that is the experience. Imagine that this experience in a human context, I come and I give you the whole experience in my life, and I tell you, you need to learn from that. It could be quite a significant task, sometimes counterproductive task, to even think that we can just collect the data and give it to the machine, and the machine will be able to learn from this data straight away. So machine teaching and some other branches of AI start focusing on this experience. And the first thing that we will be talking about is how we can actually sequence the experience. And this sits at the heart of statistical sampling theory, at the heart of machine teaching, how I can sequence this experience to the machine learner so that this machine learner can incrementally learn as efficient as possible. Now, where is this experience coming from? Normally, we will be making an assumption that all the experience need to belong to the same distribution, and because machine learning is not magic, there need to be shared knowledge in this experience that the machine learning algorithm is going to learn from. What this really means is that we have a particular class of tasks. In the example that I gave you about the self-driving car, the particular class of task was I would like to detect obstacles in the images. So it is this obstacle detection, and I am focusing on a self-driving car, which would be moving on roads and streets. And that is why we start looking at the context. So normally we fix the context. Despite that, the machine learning problem itself is an extremely complex problem. The fact is that any type of artificial intelligence in the real world will not be sitting in a single context forever. And any realistic artificial intelligence in the real world will be exposed to lots of different contexts. And that is when things start getting complicated. And that is the time we started looking at machine education, how we can structure this body of knowledge to the machine. So it's not just about machine learning. It's not just about designing new algorithms that can improve the performance of the machine. It's not just about how to present the experience to the machine, but it's about the whole cycle. If I would like to design and develop an artificial intelligence system that can operate in complex context, how should I go about doing that in a systematic way? And that is where machine education started taking off. So the first difference is in machine learning, we'll be talking about accuracy, we'll be talking about error. In machine education, what we are looking at is the skills. What skills have this AI acquired? So we shift the focus from just accuracy. Accuracy is just an indicator of performance, but it does not mean that I can conclude that this AI developed a particular set of skills. So how we can assess that? How I can say that this AI that is detecting obstacles in images, the skill it developed is it can detect obstacles of sizes between 5 centimeters to 2 meters from distance of 5-10 meters away, and so on. So what type of a skill, how I can describe the skills that this AI have really acquired, because that's quite critical when we are talking about real world situation. We don't just get a mechanic that is very good in fixing the car when we want to graduate engineer. When we would like to graduate engineers, we would like to focus on the skills that they have acquired through the education. And the second thing is we tend sometimes in machine learning that we would like to come with this deep neural network that detect obstacle, and we just talk about generalization as if it will be successful in every context. It will be exposed to detect obstacles. In machine education, we emphasize a lot contextual awareness. So based on the context, the AI might need to switch from one model to another because the model that it developed it has a particular set of skills which are not appropriate for the context it's facing, and therefore it needs to change its model based on context. The third difference is we start moving from talking about performance and accuracy to talking about assessment assurance. In the same way, when we are testing our engineer in the university, we graduate them based on a particular set of exams which test the knowledge and the skills they have developed. Some of these exams might be practical applied exams, some of them might be theoretical to test the know-how in the knowledge that they have acquired. So our focus is shifting in machine education from coming and saying, I need to mathematically prove that this machine learning algorithm is going to function in all circumstances, to accrediting the curriculum the machine learning algorithm has been exposed to. In the same way, we accredit the curriculum in our university setting before we graduate our engineering student. And the last point of difference, there are many points of difference, but I'm just giving you a good example of the diversity of points of difference between machine learning and machine education, is that in machine education, we emphasize a lot social integration of the AI. So I would like to have this AI socially interoperable. It needs to be ethical in the decision it makes. So how we can embed the ethical compliance in the curriculum that we are designing for the AI, how we can make this as part of our design instead of assuming that, for example, the ethical implication is just about testing the AI. We need to integrate it in the design from the first step. So machine education, the definition that we use is what I am showing you on the screen. Machine education, it is about the identification, organization, and delivery of body of knowledge to cognitive machines. I'm trying to identify, organize, and deliver a particular body of knowledge. In the same way, if I would like to teach a human linear algebra, that becomes a body of knowledge that I would like to teach this human. So we go and we design curriculum for that. We design lessons, we design lesson plans, we design teaching materials, we design assessments, and we sequence our lessons to the human learner such that they learn in an incremental manner. Machine education is doing exactly the same, using these theories that have been accumulated in the human education literature to give us, to shed light on how we can develop a body of knowledge for an AI, so that when we conclude learning for this AI, we can have confidence in the skills it has developed. We can have confidence that it is ethical, it is ready for human integration and human interaction. I can accredit the curriculum it has been exposed to, and so on. So when we are talking about machine learning, normally, if you look at any paper, the starting point is a very clear problem definition. But anyone who's done modeling in the real world would know that the problem definition does not come to us on a plate. The problem definition is a huge exercise that we go through just to understand what the problem is and how we can formalize this problem definition. So in the real world, we will not get a problem definition as I would like to develop a deep learning model for obstacle detection in a series of images, unless you are a machine learning expert. But the organization who gave you this problem definition has gone through significant effort to structure this problem. Now, if I would like to move into real world artificial intelligence that can operate in complex environment, I need to also take into account this problem definition. Machine education starts from the user, from the design intent of the user, from defining what are the tasks that the user would like this AI to perform. Then we have the first human expert here, which is what we call the curriculum designer. This curriculum designer will be sitting with the user, eliciting the requirement from the user and transforming these requirements into specifications that will guide the development of the machine learning algorithm. Then the curriculum designer will give these requirements, which we talk about them here as a set of skills and goals. These skills and goals will be handed over to another human, which is a human teacher for the AI. That is a human who needs to structure the body of knowledge for the AI. And this human is not necessarily a machine learning expert. This is a set of different skill sets from a classic machine learning expert whose responsibility is to structure this body of knowledge. And once this body of knowledge gets structured, it goes to the machine learner student. So it goes to the AI. I might have here machine learning expert who is helping this AI, or might have an autonomous machine learning algorithm that is able to do this autonomously. So when we start looking at machine education, we are talking about a very much multidisciplinary field. We are talking about the body of knowledge. We are talking about complexity, how I can assess the mathematical and space complexity of the requirement for the machine, for the AI that I am designing, talking about system thinking. Lots of different fields come together that I need to include to talk about machine education. And you can see that the skill set to do machine education, it is very much multidisciplinary. I have them colored here in group. So uncertainty, risks, and complexity, that's a group of skill set. The team that we need to have, system thinking and system of systems and system engineering, another set of skills in the team. Architecture and modularity is another set of skills. And obviously, the cognition component is another set of skills. Then I need to have people who are experienced in the integration, because we don't end up with a single model. We end up with a system of systems. We end up with a suite of models that we need to synthesize them and integrate them so that we can deliver on the requirement of this real world problem. So now I take you through very quickly some of the literature. You may think, oh, machine education is new, but as a matter of fact, the machine education is coming from a very long history, and that goes back to Alan Turing back in his paper 1948. He talked about machine education. But he had a very small section. And if you read what I have on the slide, if what he is saying is, if we are trying to produce an intelligent machine and are following the human model as closely as we can, we should begin with a machine with very little capacity. So what he is saying is what I will talk about in the next slide, as what Illman in 1993 talked about, the importance of starting small. Start with something that will require little capacity from the learner to carry out elaborate operations or to react in a disciplined manner in orders taking the form of interference. Then, by applying appropriate interference, mimicking education. So what he's saying is, let us get the smallest machine that can do the task on a low level of complexity. And once we get this right, let us follow a systematic way that we apply interference in the same way as a teacher in the classroom will start exposing students through a systematic sequence of lessons so that the student over time learn more complex lessons. That's what Turing said in 1948. But he said, this would be the beginning of the process. I will not attempt to follow it further now. We did not have the advances in AI that we have today at the time. We did not have the computational infrastructure that we have today at the time. And so we did not really have the technology to allow us to do what Alan Turing was talking about. Now, if we start moving in time very quickly, we will get to see significant amount of effort that has followed the steps from Alan Turing. Incremental learning, the idea that I have a machine that might have learned a concept, and now I would like to keep adding to it. Active learning, having a machine that can dynamically and potentially in an automatic way can identify what it is missing, which part of the spaces of the state space that it may have missed, or maybe it is not performing as well, and it actively seek the experience that allows it to improve its performance. And the famous Elman paper, the importance of starting small, again, talking about what Alan Turing was talking about. Let us start small, but the devil is in the details. The real question we need to ask ourselves is, what do we mean with small? What do we mean with sequencing the complexity of the learning process to the machine? How can I transform that into mathematical metrics that can assess the true complexity? Because what we believe is easy could be the most difficult thing for the machine. So the word small here should be looked at with significant care. Then in the recent literature, starting from Bengu, the curriculum learning approach, the idea of designing these lessons and sequencing them to the machine. And there's significant literature on this topic. Machine education comes and synthesizes that into an overall systematic methodology so that we can design complex machine. And that takes me to my next point in the discussion. So far, we may have advanced AI so that we have very interesting, powerful deep learning model. But this is what I will still call simple learners. The problem definition is very clear and it's very precise. And what the AI is learning is a particular class of tasks. This AI is not learning how to live in the real world. This AI could be just learning how to detect obstacles in an image. In a self-driving car, it is not just about detecting obstacles. It's not just about detecting lanes. It's also about navigation. It's also about autonomic computing, the ability of the agent or the AI to self-assess itself, to look after its own internal health and monitor its internal systems. it is much more complex than just detecting an obstacle in an image. That is, we are still in machine learning operating in this space of simple learners. Complex learners, the problem definition is different. You have a user who come and say, I would like a self-driving car that is going to operate in a busy city. That becomes a problem definition. I would like to make sure that this self-driving car is going to operate ethically. I would like to make sure that it's going to be safe. I would like it to follow the local regulation and law, and so on. So now I have set of requirements which are quite complex, and they are not about designing a single machine learning model. It's really about designing the system of systems of machine learning so that we end up with an AI that can look after a self-driving car. So I will give you very quickly contrasting the simple learners against the complex learners. When I'm talking about simple learners, I am most of the time talking about homogeneous skills. Even when we talk about multitask learning, which I will have in a couple of slides, it is still homogeneous set of skills. Complex learners are about heterogeneous skills. Simple learners will deliver single or ensemble of models. Complex learners will have embedded learners, will have learning machine within learning machines. Simple learners, the type of skills that I need to have, the human skills that I need to have, would be computer scientists or engineers. In complex learner, I need to have multidisciplinary skills. I need to have people who work in ethics, people who work in the legal domain, people who work in system engineering, people who work in human education. It is normally a very diverse, multidisciplinary team. I'll be talking about linear or simple nonlinear fusion of learners and simple learners. In complex learners, the fusion problem is quite complicated and it's heterogeneous and highly nonlinear. In simple learners, I will be talking about simple or abstract context or single type of context. In complex learners, we talk about realistic contexts which are made of many situations, heterogeneous situations. So I will give you an example of our own work that we had almost now 16, 18 years ago. We looked, for example, at robotic tasks, and what we needed to do is to be able to design the body of the robot in conjunction with the controller of the robot. This is a complex, this is not an easy machine learning problem. Anyone who works in this domain will understand that. There is instability in the controls that we have. You can see here the body does not have fixed shape. It is actually co-evolving with the controller. So you end up with behaviors like this one, where it's almost like a kangaroo. It looks nice, but the controller could end up to be unstable, and we could actually we sometimes you may discover that while it is successful, for a little bit it will start failing and so on. We have some real complex issues in machine learning that we still need to solve, but this is still what we will call simple learners. Another example, another more recent example, with some of our students, we looked at multitask learning. But again, when you look at the multitask, you will find that they are homogeneous from the class perspective. So still, while we are still talking about multitask, they will still fall within the simple learner. That is a hierarchical deep neural network architecture which combine different type of sensor data, LiDAR data, as well as images. And you engineer the architecture for that, and it's not an easy problem. There are problems in machine learning that we don't have solutions for still yet, but it is still falling in the simple learner. Now, I will show you an example of one of my favorite problems, but it is a complex learner. Despite that the problem will sound simple, you will discover that we don't actually have a machine learning model that has learned from scratch in the literature how to do this shepherding problem efficiently. We don't have such model. We use lots of domain knowledge to design the machine learner that can do that. So shepherding is simply, I have a sheepdog that needs to collect sheep. So that's one of the sub-problems in shepherding called mastering. So the sheepdog will need to go and collect the sheep and take them to a particular goal. Why this is complex? Before I tell you why it is complex, let me tell you what it is useful for. It is useful for lots of applications. It's useful for agriculture. The idea of herding was used to increase safety in the airport area because there are lots of birds that are flying, and using these people using a UAV to steer the birds away from the aircraft so that you increase safety in the airport area. Cleaning under ocean, and obviously nanomedicine, how we can guide nano robots inside a bloodstream so that they can, for example, go and deal with cells like cancer cells and so on. So there are significant applications for this type of problem. But on its very simple level, this problem can be described with very two basic skills that the AI need to develop. The first one is what we call collecting skills. Well, I have one sheep here outside the flock. So the AI, which is in blue, that is the sheepdog, it needs to decide how it will steer this astray sheep back into the flock. So it defines what we call the collecting point. It moves to these collecting points. Then it steers this sheep back to the flock. Once the sheep are collected, it defines what we call the driving point. It goes back to the driving points and it steers this flock to the goal area. You look at that and you think, this is very simple task, but as a matter of fact, the two skills that I just mentioned, there are other skills which you need to have. For example, this sheepdog should be avoiding the sheep as it's going to the collecting point and the driving point so that it does not disturb the flock. These simple skills operate on different state subspaces. And because of that, this problem is quite complex. And once you start adding more dogs to the problem and you start increasing the complexity, you discover that the problem gets extremely complex. So we managed to do machine education very quickly, showing you here a couple of videos where we managed to solve this type of complex problems, and we prototype them with my collaborators in different environments, high fidelity simulation environments, robotic environments, and so on. So that is that's what I wanted to explain to you in detail, that machine education is really the next big thing in AI. If we would like to take AI to the real world, we need to think beyond machine learning. We need to think about the system of system problem. We need to think about the social integration of the AI. We need to think about the requirement, the specification, how this AI is going to interface with humans. We need to think about the bigger picture, because without that, our machine learning model will continue to be operating in the lab and they will not be applied. So I will now very quickly take you through lots of different slides. Mainly, I will talk to you about some of the work that we've done in this area, some of the principles that we designed. I will talk to you about two use cases that we have published on. and in a hope just to expose you to some of the recent development in this domain. So the first thing that we needed to establish is we need to establish principles for what we mean with machine education. And we came up with these 8 principles. We call them educates, and we had lots of thoughts about how to name them and so on. And one of our collaborators was quite genius, came up with this educates to abbreviate the first letter in each principle. So let us really quickly look at some of these principles. When we are designing an AI, we are designing an AI to be used in the real world. This AI will either be interfacing potentially with another AI or a level of automation in the system, or will be interfacing at some point with a human in the society or a human user. So we need to emphasize the role of the human AI teaming from the beginning. So I will give you examples of some of the work that we've done in this area very quickly. But the first principle is about exemplifying a blueprint for human AI teaming. One of the requirements, obviously, is to have a transparent and explainable machine education framework. The machine education is not useful if we end up with a set of mathematical algorithms that the user does not understand them. Machine education is about integrating the AI with the wider user community, and therefore it's extremely important that our frameworks are transparent in themselves and explainable to the user. And because of that, we rely on lots of theories from the human education literature, because there are significant amount of work that happened in this literature that could assist us. So using education theory to graduate machine learners, I normally talk about that as the future university. We need to establish universities for AI, where the student is an artificial intelligence. Some people see this as science fiction, but what I am really talking about is how we can actually develop AI by humans who are not expert in machine learning. How I can teach this AI in a similar way that we are teaching human. So I am talking about the scientific discipline of curriculum design, curriculum learning, and the wider discipline of machine education than science fiction here. Uses well-established education theory, as I said, and it needs to contribute to the wider society. That's where the social integration comes. And another 4 principles, which if you are interested, you can look at our paper. They are being explained quite clearly in our work. So let me share with you some of our recent examples here. That's one of our most recent paper, actually looking at communication language between the human and the AI and how we can actually design this. That's a whole problem in itself. How can the AI talk to a human? What language should we be designing? And what type of architecture this AI need to have to enable it to interact with the human while it is able to interface with all the models that it has developed? The problem of transparent AI, we needed to actually model this problem in a very concise and precise manner. There are lots of philosophical debates about what is transparent, what is explainable, what is predictable, what is controllable, all of these concepts. And it is really important to have these philosophical debates. But if we would like to design the algorithms, we need to contextualize that into the mathematics, and we need to be able to connect these formal definitions in such a way that we can transform them into the mathematics of the machine learning algorithm that we are using. And to give meaning, to be able to explain what's happening in the AI, this area of ontology, it is somehow forgotten, except for some of the recent literature. Some researchers start looking at ontology-guided machine learning. We had papers on ontology-guided machine learning almost 18 years old now. One of the first things that we've done in this domain was ontology-guided clustering. And I remember very well at the time, people were saying, why do I need to have an ontology guiding clustering? I can tell you why in a much longer talk. But how we can move from the ontology to modular design of some of our black box models like neural networks. Our paper in SSCI 2019 give a hint on how to do that with a very trivial ontology here that we transformed into sub neural network that we integrated them into a much larger neural network. So how we can design this complex neural network guided with ontology. And what does this allow us to do? We can also go the other way and ask, what does the neural network do? So we need to understand what the network is doing. So some of our recent work has been looking at this interpretable neural network. The last thing I would like to share with you is two use cases very quickly. One of them is about shepherding, which is a 2019 paper, and the second one is about swarm intelligence, which is a 2022 paper in the Journal of Swarm Intelligence. So we use different type of curriculum design methodologies. So each paper actually used different curriculum design model. In the 2019 paper, we used George classical curriculum design, quite well established and old model in human education. And it's really important to say that because old models in human education have never been applied to AI. So the fact that they are old in the human sense, that's because the humans are far more advanced cognitively than the AIs that we are using today. So some of these old models are extremely useful because they are very well structured for AI. So George classical curriculum design has this characteristic, and we went and we really designed solutions for shepherding by taking the problem, decomposing it into skills, and designing models for the individual skills. We analyze the complexity of the problem in the bottom left graph, and we compared our curriculum approach against a non-curriculum approach to measure the advantage of using machine education. It's not just about having a systematic, transparent methodology to build the complex behavior, but it also comes with advantages that it does this very efficiently. Another model which is used in our 2022 paper in the Swarm Intelligence Journal is a Dick-and-Carey model of curriculum design, and that was used to solve a problem called best of n problem. So the idea here is that I have the swarm in this grid-based environment. This environment has black cells and white cells, and the swarm need to fly or move in this environment, and at the end they need to make a decision. Each of them need to make a decision individually, then collectively. Do we have more white cells or black cells in this environment than the other color? So for example, if the majority of the cells are black, we need to say the majority of the cells are black. This sounds as a very, very simple problem, but when you start decomposing the skill, you discover that there are lots of sub-skills here. So we decompose it into 4 sub-skills. And some of these skills are quite difficult to learn. But what machine education helped us to do is to structure the problem space so that we can actually design the machine learning in an efficient way. So I will conclude here by simply giving you 3 take-home messages, and all of them are really centered on machine education. I totally believe as we keep trying in machine learning, developing new models, at some point we need to start taking this to the real world, not just on applied problems in the lab. And that is the time that the community will start working more and more. There is a growing community. It happened in the last couple of years in machine education. I'm expecting that there will be more people growing different methodologies for machine education. So if you really would like to start working on the future of AI, I think one of the topics that I would recommend to you is to start looking at machine education to contribute to this future. I would like to thank my funding agencies, and I would like, before I conclude, I can't really conclude without inviting the listeners, whether you are on the webinar or whether you will watch this video when it is made available on the IEEE website. You are all invited to submit to the transaction on artificial intelligence. This journal started almost 2 years ago, but it has grown super fast and with very large number of submissions today. So if you would like to position yourself in the field of artificial intelligence, that is the journal that you should be looking at. With that, I would like to conclude and thank you for listening to me, and thanks for IEEE for hosting this seminar and the Computational Intelligence Society, and a very, very, very happy IEEE Day to everyone. Thank you.
Okay, thank you very much, Professor Hussein. So I have a question from Professor Jim Keller. He asking, why is ontology guide clustering a hard problem?
That's a very good. It's really an excellent question, Jim. Thank you for asking that. If we start looking at clustering itself, and you know this better than I, there are clustering in Euclidean spaces is almost like a solved problem, but when we start looking at higher dimensional spaces and we look at other type of clustering, fuzzy clustering, and so on, we still have problems in clustering itself. But the ontology guided clustering, just to explain it very quickly, if we just look at something like k-mean clustering, what we are using to design a k-mean clustering is a mathematical metric of similarity, which would be, let's assume, an Euclidean distance. So we end up with cluster, but at the end, when we look at this cluster and we would like to understand what should we be labeling this cluster, we may discover that it is really difficult because the concepts that we are familiar with as humans are not encoded in the similarity metrics that we use to do the clustering. So we get clustering that are extremely difficult to really assign meaning to them. Well, as with ontology guided clustering, the ontology guided clustering come and say, okay, let us think about the clustering from two perspectives. One is there are a series of concepts that I understand from the domain, and I know their relationship to each other and their connection to each other, and I also have these magnificent similarity metrics in mathematics that I can use to guide my clustering. Why don't we get them to operate together? Why don't I get the ontology to do some guidance, to do some correction these two documents might be close to each other in the similarity, according to the similarity measure. But maybe according to my understanding of the contents based on the ontology, they should not be next to each other. So can I use the ontology to correct my similarity measure? And can I get the similarity measure to tell the ontology you might be missing some concepts and you need to add more concepts? And that's what makes the ontology guided clustering a hard problem. How to interface and how to integrate the ontology with the similarity measures that we are using, how we can couple this so that they can inform each other. I can see lots of potential here for fuzzy. Surprise! In computational intelligence society, we have a whole field which could actually help significantly in contributing to this problem. And I would really hope to see lots of papers in that domain. But the hardest question to ask, in addition to the classic difficulties with clustering, is how we can integrate the ontology with our similarity metrics.
Okay, thank you so much. I don't have any more questions. An audience asking if he can get a slide. So I think he can send you an email later and asking question or asking for slide later on, right?
Yes, please. And the talk, as far as I know, will be also available on the IEEE CIS. So the whole video will also be available at some point.
Okay. I think we should stop right here because I don't have any more questions from the audience. And thank you so much, Professor Abbas. So this is a pretty good presentation. So good night, Professor Abbas. Is pretty late for you, right? So good day, everyone, and good night, everyone. So I'm just gonna stop right here. Thank you so much.
Thank you.